Hello everyone. Today we're gonna look at another LeetCode problem. This is problem 62, 62, 60, 62 unique parts. There is a robot on an n times n grid. The robot is initially located at the top left corner, i.e. grid 0, 0. The robot tries to move to the bottom right corner, i.e. grid m-1 and -1. The robot can only move either down or right at any point in time. Given the two integer n times n, return the number of possible unique paths that the robot can take to reach the bottom right corner. The test cases are generated so the answer will be less than or equal to 2 times 10 to the power of 9. Alright, so let's look at sample 1 there. So we have m equals 3 and n is 7. So the output is, I think we can use a 10 choose 3. So this is 10 factorial divided by 3 factorial divided by 7 factorial. So this is 10, 9, 8. So this would be give us 3 times 2, then 3, 30, 120. Oh, sorry, it's wrong. It's not 10 choose 3 actually. It's 7 plus 3 minus 2. So 8 choose 2. So that would be 8 factorial over 2 factorial, 6 factorial. Then this is 8 times 6, 7. 8 times 7. Divided by 2, so 28. Problem 2. We have 3 times 2, so this would be the same as 3 choose 1, so that would be 6. Nope. 3 choose 2, so yeah, just 3, sorry. Okay. I think I got the problem now. I would like to clarify a few things. Yeah, what is n times n? So we're given that n times n is from the range of 1 to 100. So we know that n times n is valid. And alright, I think that's about it. I think a very quick approach is to use this formula where we just take a factorial. Yeah, I mean we can use the combinations formula, which is the m plus n minus 2 over m minus 1. So this would actually becomes m plus n minus 2 factorial divided by n minus 1 factorial, n minus 1 factorial. So then this would be the same as I think that's it. I think this is one approach. But here we are trying to work on a dynamic programming solution. So what we can do is that, so let me just, I'm thinking that it should be a quick way to do this. Python factorial. Import method factorial. Okay, so let me quickly input this particular solution. So that is sound reasonable. I would like to start implementing, but I'll just ignore this later on. I'm just doing this for fun, basic. So import met, and then I'm gonna return all the factorial there. So met dot factorial of m plus n minus 2 divided by met dot factorial n minus 1 and then n minus 1. Okay, so let me quickly put the solution into there. Met and then return met dot. Actually, let me just import it from met import factorial then we return factorial of n minus 1 plus n minus 1 divided by factorial of n minus 1 divided by factorial of n minus 1. And this works. So let me try to submit it. Yep, we got it right. But in terms of dynamic programming solution, if you want to work on the dynamic programming solution, then what we could do is that we use a dynamic programming, or more specifically, we use a two-dimensional dynamic programming. First of all, we take the grid, and then we try to find how many ways there are to get to a particular point. As a base case, if we look at just m, m is 1, then there is only one way, which is the robot moves to the right all the way to the end. And then if we try to expand our problem into a more complex one, i.e. we set m equals to 2, then we can see that the number of ways has increased. Basically, the robot can go down and then go right, or it could move right and then goes down, go to the right to the ends. And we see that so if we have just one square, then output is 1. If we have 2 by 1, then there's still 1. If we have this square, then it's still 1. If we have 2 by 2 square, Then there are two ways. If we expand it further, we have 2 by 3. So this one has 1, 2, 3. So 3 ways. So how do we know that there are 3 ways here? Basically, we can split the problem further. So if we look carefully in the box, we can fill in how many ways we could achieve that particular box. So when I fill in here in 2 by 2 box, the way to reach the finish box is there are 2 ways, which is from left and from the right. And then same for the 2 by 3 box. The number of ways to reach the particle is the one that I have filled in here, which is basically the summation of the previous boxes. So if I write the recurrence function, that will be fxy equals to f of x minus 1 y plus f of x comma y minus 1. Okay. So I think this sounds reasonable. Does this sound reasonable? Does it look reasonable to you? I feel pretty good about this, and I would like to proceed to programming unless there is further optimization that you would like me to explore. Okay, I guess now one way we could do this is we create a array of size m, and then we basically uh, use it um, use it use it at turn, and then we try to reuse the array so that we don't need to build the entire matrix and then fill in the box like I have shown before. So let me just call it the prep initialize to the prep. I will like initialize to 1 because there is only one way to read if there is only like a one straight line, then there is only one way to reach all of the boxes there. So basically prime would be 1 of the size of m, and then curve I'm gonna fill in, say I'll just put 0 for now. Actually, for simplicity, let me just expand it by 1 more. So instead of m, I will put m plus 1. And this is actually for easiness when we implement our function there, because if we add an additional box there, then we don't need to take care of all the edge cases where we are at the, say, first column. Or actually, when we look through later, we don't need to check the first column. Okay, I think that makes sense. We don't need to create an additional box. That is just it's not, there's just one minor technical details there. I mean implementation details. So yeah. And then now you're gonna look through I in range. You're gonna look through the n. Actually, so I look through the n minus 1. Yep, I think so because the first one has been filled out by the prep. Then now, what we need to do is I think I don't need two array here. Yeah. Okay, let's just use the prep. So let me cross out the curve. And then now you're gonna look through for I in range, I, comma. So we can skip the first one because it's always gonna be 1. And then we look from 1 to m. And then we fill in the prep of I equals prep of the current one plus prep of the previous one. Yep. So we can think of it as the prep I is the f x of y minus 1, and then prep I minus 1 is f of x minus 1 comma y. So that would work. Then finally we return the prep of the last column. Okay. Alright, let me go to the code again to make sure I don't miss anything. And create an array which is initialized to 1. This will represent um, the number of ways to reach a particular cell. If the number of ways to reach the particular cells at the first row. And then I'm gonna reuse this array as I work on the second row towards the end. So now I create a for loop for the second row towards the end, and then I fill in one by one. The formula there of prep I is the same as what I specified before in our recurrence function. Then in the end, I just need to return the last column. Okay, so let me test the code with our examples then. So number 1, we have prep of 1, 1, m is 3. Actually, we can skip, we can flip the m times n so that we could use the smaller one. So let's take m equals 3 here. And then I'm gonna keep updating. So for I to n minus 1, so there are 6 of them. So this will be 1, 2, 3, 1, 3, 6, 1, 4, 10, 1, 5, 15, 1, 6, 21, 1, 7, 28, 3, 4, 5, 6. So that will be it. The answer is 28, which is correct. Second one, we have 2 there. So 1, 1, so 1, 2, and then 1, 3. So answer is 3. So I think that will be it. Now let me input our solution there. So curve equals 1 times minimum. So if n is smaller than m, then n equals n, because I want the smaller one so that I don't use a lot of memory. In that sense, then I'm gonna look through all of it. I'm in range, applying in range n minus 1, or I'm in range 1 to n. Then 12 of I plus equals 12 of I minus 1. Then we just return the last one. Then this would be it. Yep, let's try to submit it. We got it right? Yes, we got it right. Alright, I think this would be it. So thank you everyone. We're gonna stop here for this problem.